So we're going to cover two things, differentials and linearization. We're actually going to start with the linearization, which is more applicable to more of the stuff. See, I see questions like this as part of AP tests all the time. Usually it's kind of like a little tag question at the end. Oh, we have this 9-point question, but we only have 8 points worth of stuff in it. Let's slap this stupid little thing on the end to add an extra point, or make it 2 points. And it kind of relates to this in many ways. And this is one of the things that calculus is kind of useful for. Okay, approximating values of a function without actually having the function. Okay, what are the approximate of the function? So the idea of linearization is you're writing a tangent line equation. Linearization is just another way of saying tangent line. That's it. That's what a linearization is. It's another version of the tangent line. And you're going to use that tangent line to approximate. So if I replace L of x with y and f of a with y sub 1, you have the point slope version of the equation. Because what is f prime? F prime of a is the slope at that point. And a is, the x coordinate of that point. F of a is the y coordinate. X coordinate, y coordinate, slope. What do you have? You have the equation of a line. That's what this is. Just taking the point slope version and rearranging it. So you have y equals y sub 1 plus the slope times x minus x sub 1. That's all it is. It's a rearrangement of the point slope version of the line, which is a tangent line, y equals. That's what linearization is. Okay, so what do you need to write a line? You need three things: x coordinate, y coordinate, and slope. X coordinate, y coordinate come from the original equation. You have to be given one of those. Usually it's the x. Okay. The slope comes from the derivative at the x coordinate. So that's your first step. So suppose f of x is negative x squared plus 4, and I have a graph here that shows that. Find the linearization at x equals 1, which actually I have that graph here already. That's the tangent line. The linearization is the tangent line. So, okay, I need a couple of things. I know x equals 1. I need to find f of 1, i.e. my y coordinate. So I plug in y into the original one, and I get 3. X coordinate, y coordinate. And the next thing I need is my slope. I need f prime of 1. Well, to find f prime of 1, I need to know what f prime of x is. I have to take the derivative. F prime of x equals negative 2x. So f prime of 1 is negative 2. Right? Piece of cake. Plug those three things into the formula. So my linearization, L of x equals y sub 1, or my y coordinate, 3, plus negative 2 times x minus 1. And to make it all pretty, you should rearrange it and simplify it and put it basically in mx plus b form, right? Okay. Let me slide this up. So I get L of x equals negative 2x plus 5. Is that right? Does that work out? Yeah. So that's the equation of this line here. That's the linearization. Now, remember, it's very important to remember, I can use my tangent line to approximate my curve, but I can't do it very far away from the point of tangency. Okay? It's not going to work at x equals 0. At x equals 0, that's not very accurate, is it? Okay? But at x, so here at x equals 1, okay? When x equals 1, I can go, all right, no problem, and take a look at it and say, hey, I can approximate that with 1.1 because 1.1 is very close to 1, and I can use my straight line to figure out what my equation is. So I want to do my approximation. L of 1.1 equals negative 2 times 1.1 plus 5. So 5 minus 2.2. 5 minus 2 is 3. 3 minus 0.1 is 2.9. 2.9. Now you say, okay, why would I do that? I can take 1.1 and plug it into the original equation, right? Okay, so if I take 1.1 and square it, what do I get? 1.21 negative. Subtract it. See what I'm saying? This is a relatively simple equation to take the derivative of. And a relatively simple equation, or I should say, a relatively simple equation to actually take 1.1 and plug it in. But what if your original function is something really nasty, ugly? And you're like, I don't want to deal with that. Taking the derivative at a particular value may be easy, where evaluating the function itself, if something just a little bit off that might be difficult. Does that make sense? That's why you kind of want to do this. We, in this level of calculus, we approximate curves with straight lines. One of the really cool things is if you get into second semester calculus, we don't do it in here, but if you get to the BC, the stuff that the last couple of chapters of your book that we don't get to, they actually approximate curves with other curves. So you take this really funky thing and approximate it with a polynomial. So you got a curve approximated by a curve. That's a lot more accurate. Why would you do that? Because the polynomial is easier to work with than whatever that funky function you had to begin with. That's why we do this. It's so much easier to work with a straight line than it is with a curve. That's why. Because we're lazy. And in the immediate region, a curve is a straight line. So if we're close enough to our starting point, it's close enough for government work. That's why you use this. We're approximating it. I know that's not the exact answer. It's close enough for anything we're going to do. Okay, and that's the idea behind it. Take something hard to work with, come up with something easier to work with instead. That'll work nearby where we're at. That's all that is. That's what that whole point of that whole thing is. Okay? Yeah. Yeah, 2.8. You're right. My bad. Thank you for pointing out my mistakes. Oh, yeah.
It's on video.
Yeah, it's all recorded. It's all good in the hood. Actually, I was counting yesterday when I was doing my lectures yesterday. I was counting. I made 5 mistakes all day long. They're all 5 stupid mistakes, too. Just like that one was. Okay, differentials. That's a little more difficult, but it's not that bad. Okay. Let y be a y equals f of x be a differentiable function. You can't work with differentials if you can't take the derivative, i.e. it must be differentiable. Say that 5 times fast. Don't do it. The differential dx is an independent variable. The differential is dy equals f prime dx. The idea is you're trying to find, if you know what the change of x is, what's your change in y? What's your corresponding change in y? X changes so much, how much does y change at the same time? Because a function is a relationship between x and y. And if I change x, how does y change? That's what the whole point of this is. Relating the change in x to the change in y. So if I change x by this little bit, how much does y change as well? Okay. So if I normally, if I start out at the point 2, 1, and I move the x coordinate a little bit, how much does the x coordinate move? That's what that's saying. It doesn't tell me what my new y coordinate is. It just tells me how much it moved, how much it changed. Okay, and this is a big tie to what we're going to be doing when we come back from break. Okay, so let's do this together. It's actually really easy. The formula for it's right here. dy equals f prime of x dx. So if y equals x cubed plus 12x, okay, write out my differential. dy equals 3x squared plus 12 dx. That's the first thing you do. Take the derivative. Take the derivative of both sides. Kind of like if you were doing implicit differentiation, but you're not going to solve for dy or dx. Okay, but that's kind of the step you do here. Step number 2. Plug in 2 for x and plug in negative 0.05 for dx. And figure out what dy is. So dy equals 3 times 2 squared plus 12 times negative 0.05. Why is it negative 0.5? Because I told you it was negative 0.05. Because you're given that information. So I start my x coordinates at 2, and I move it negative 0.05. How much does my y move? If I change my x value this, how much does my y value change? It doesn't tell me anyone, this tells me how much it changes. That's the idea. So please, somebody pull out a calculator, because I don't want to multiply by 0.05, negative 0.05. Negative 1.2. I hear negative 1.2. Do I hear more than that? Okay, this 2 decimal places, and I think it's negative 1.2 even, right? Yeah. So a tiny little change in my x makes a great big change in my y. Does this make sense? If you look at the equation, I got x cubed and I got 12 times x. If I make a tiny little change there, yeah, because I'm cubing my change. Amongst other things, my difference is going to be cubed on that one. Does that make sense? And this starts into getting into what we're going to be doing and come back is, how does a change in one thing affect a change in something else? That's really what this is about, is introducing that concept of, if I change this, how does that change? Because changing one thing affects something else. Think about your physics and the pressure, volume, and temperature. If you hold one at a constant and change something else, you've got to change in the other one, right? That's kind of the idea. If I change this, how much does that change? No, we will not be working with pressure, volume, and temperature, but you get the idea. Okay, your turn. Give it a shot. Okay, first step, take the derivative. dy equals the derivative of the tangent of 2x. The derivative of the tangent is secant squared. The derivative of 2x is 2. Remember, this is a chain rule problem. So I get 2 secant squared of 2x dx. Okay, chain rule problem. Now I need to find dy using pi for x and 0.1 for dx. dy equals 2 times secant squared of 2 pi times 0.1. Okay, secant is 1 over the cosine. Cosine of 2 pi is 1. Yes. 1 over 1 is 1. 1 over 1 squared is 1. 2 times 1 is 2. Almost got you on that one. Times 0.1 is 0.2. dy equals 0.2. Ha! And I didn't even need a calculator to figure that one out. See, if you know your unit circle really, really, really good, you don't need your calculator for everything. Okay? Now, last but not least. Okay.
Do we need a lot of room for this?
No. Well, you might need a little bit of room, but hang on. Okay, what was that? Question, or just didn't get the information down in time? Okay, sorry. Just little elevator music in my head. Did I do that out loud?
Yeah.
Okay, sorry.
Yeah, seriously.
It's my favorite elevator music. Girl from Ipanema. I know. Okay. So the radius of the circle increases from r equals 10 to r equals 10.1 meters. Use dA to estimate the increase, and it says estimate, the increase in the circle's area A. Contrast this with the true change. Now, much of this work has been done for you, but I want to talk about a couple things. This is almost what we're going to be doing when we come back. So, introduction to what we're doing when we come back. dA stands for actually what? And how would you understand and know so much about the criminal system? Huh? Are you intimately involved with it somehow? I know you're juvenile, so all your records are sealed. Oh, now it counts, huh? I always like the question, have you ever been convicted? Convicted? No. Okay. No, dA stands for, what does A stand for? A is for the area, right? So dA is the change in area. So what we're trying to do, we're trying to find the change in area. dA says, what's your change in area? What is the change in area in relationship to the change in radius? If I change the radius, how does that change the area? So what I need to do is I need to take the derivative of the area function. The area derivative of A is dA. The derivative of pi r squared is 2 pi r dr. Okay. Because what am I taking? What's the variable? R. Okay. So what this does, what I have now, my top equation is an equation that relates area to radius. My bottom equation relates the change in area to the change in radius at a particular radius. That's what's happening here. How does my area change if I change my radius? That's what this is. That's what this function is. It's a function that says I changed my area. How does my area change if I change my radius? Doesn't tell me the area, just tells me what its change is. Okay. So, if r equals 10 and dr equals 0.1, the change represented as I go from 10 to 10.1, right? That makes sense. Dr is the change in radius. My radius goes from 10 to 10.1. What is the change? It's 0.1. Okay. There's our equation. We took our equation, plug in the values. Our change in area is 2 pi. So when our radius was 10 meters, and we went from a radius of 10 meters to a radius of 10.1 meters, the area changed by 2 pi meters squared, so units of meters. So the area changed by 2 pi square meters. That means whatever it was, it's now 2 pi square meters bigger. I don't know what it was originally. It's not like we can't go figure that out, but you understand what I'm saying. It changed. That was the change that happened. That's our estimated change. That's our estimated change. We can figure out the actual change. Okay. So our estimated changes here. Our true changes, figure out what it is at the new radius, 10.1, subtract what it was at the old radius of 10, figure it out, 2 pi plus 0.01 pi. We were off by 0.01 pi from the actual change. We were off by 0.03 square meters. That's not too bad, is it? Considering, you know, we went 1/10 of a meter, which is how much? 10 centimeters, a decimeter, right? Not that much. We increased the radius by that much, and our estimated change in area was only off by that much. That's not that bad, is it? Okay, it works good. Now, if I use the same formula for going from 10 meters to 11 meters, it wouldn't be nearly as accurate because that's too large of a change for it to be accurate. Okay, and I'll scroll down, try to give you, if I can, the rest of it. Okay. Any questions? This last little bit really isn't that big a deal. Okay. I'm not going to worry about the approximated percentage change. Don't worry about that part. Just kind of get an idea of what we're talking about here. Okay?